Hello, everyone. Today we're going to talk about edge-weighted online bipartite matching. This is joint work with Zhiyi Huang, Runzhou and Morteza Zadimoghaddam. So the outline of the talk is there's roughly going to be three parts: an introduction and kind of setting up the problem, a discussion of the main technique in the paper called online correlated selection. It's kind of the key ingredient that allows us to achieve our main theorem. And then we'll also go over the algorithm and analysis at a pretty high level, but to give context for a future read. So we'll start with the introduction. Edge-weighted online bipartite matching is the following problem. So the algorithm is given as input a bipartite graph with edge weights in such a way that the left-hand side vertices are offline and known to the algorithm in advance. The right-hand side vertices, however, arrive online one at a time. And so when an online vertex arrives, the edges that are incident to the offline vertices are revealed to the algorithm along with their edge weights. And then the algorithm has to irrevocably make a decision about that vertex, whether or not to match it to an offline vertex, and if it does, which one. And so we'll go over kind of a simple example that'll be the toy example running throughout this talk. But suppose this is the graph, and for now we'll just think of it as an unweighted bipartite graph. The left-hand side vertices are offline, and then there are two online vertices. At the beginning of this process, the algorithm knows nothing about the future, so it doesn't know what's coming its way. When the first online vertex arrives, the algorithm sees that it's matched to both offline vertices and has to make some kind of decision about what to do with this. So let's say arbitrarily, it takes the top edge. And so now that this match is fixed, and the algorithm has taken this, and it's an irrevocable decision. Now the second online vertex comes, and its edge, it's incident to one offline vertex, and it's the same that we matched with earlier. So the algorithm can't do anything about that. It's blocked in some sense. And so the final cardinality of this matching is 1. But in reality, we can see that had the algorithm chosen the lower vertex the first round, then it could have achieved a cardinality matching of size 2. So this kind of highlights the difficulty of online matching in some sense. You don't know anything about the future, but you want to maintain some kind of guarantee throughout the process. And the goal in the edge-weighted case is to maximize the total weight of the matched edges. So it's a generalization of cardinality to edge weights. And so how do we measure the performance of an online algorithm? We do so with what's called the competitive ratio, and we'll denote it throughout this talk by capital gamma. And the competitive ratio is really the minimum over all bipartite graph instances and all possible arrival orders of the right-hand side vertices. And what it is the minimum over the expected output of the algorithm divided by the optimal assignment of that algorithm kind of in hindsight if you did an offline computation. And so the model that we work in is the oblivious adversary model. The adversary here must fix the input graph and the arrival order of the offline vertices in advance. So it can't react to the outcomes of the random decisions of the algorithm over the course of the arrival of the vertices. So everything is fixed in advance, and it's worst case over this. Now, the first observation is that for the edge-weighted bipartite matching problem, we need an additional assumption to be competitive. In particular, this problem is equivalent to, or it's a generalization of picking the maximum element from a stream of numbers that arrive online. But we can't do that unless we can somehow replace a previously chosen number, because a greater value might come later. So what we do is we introduce, well, we don't introduce it, but we make use of what's called the free disposal assumption. And in particular, it's the following. An offline vertex can drop an assigned edge for free to be matched with a new heavier edge that comes in the future. And so this free disposal idea was introduced by Feldman et al. In the Wine paper in 2009. And it was motivated by a display ads allocation problem at Google. And in particular, kind of the relevant economic context here is that advertisers don't mind being assigned more, especially higher quality impressions, which are really just kind of displays of their ads, than they paid for. So it's okay to receive more, but you want to at least guarantee that you have something. So everything that follows from here onwards makes use of the free disposal assumption. So some related works to ours, in particular, sort of the natural sort of subset difficulty inclusion of bipartite matching problems are the following. The first related work in the adversarial case, this is really the seminal paper that sparked online bipartite matching, but it's the paper of Karp Vazirani in 1990. And in this paper, they give an optimal algorithm for unweighted bipartite matching that achieves 1 minus 1 over e. And also they have a hardness result showing that 1 minus 1 over e can be beaten. That is the upper bound. 20 years later, The vertex case was studied by Agarwal et al. The vertex case here means that the offline vertices have vertex weights, and the goal is to maximize the sum of matched offline vertices, the sum of their edge weight, the sum of their vertex weights. Again, a competitive ratio of 1 minus 1 over e is kind of now known for this problem. And yeah, so the edge weighted case, however, it's a generalization of vertex weighted case. It's folklore result that the greedy algorithm gives a 1/2 competitive ratio. An upper bound better than 1 minus 1 over e is not known. But this work in particular kind of goes a little past greedy. We augment greedy in some way. And we show that a 0.5086 competitive ratio is achievable. So in particular, greedy is not tight. And this is in contrast to the even more general problem to edge-weighted online bipartite matching called online submodular welfare maximization, where the greedy algorithm, again, is known to give 1/2. But then several years ago, a couple of Post and Fahrbach showed that an upper bound of 1/2 is also a thing. And so the greedy algorithm is in fact tight for this problem. So assuming p not equal to mp, it's our algorithm can be seen as like strong evidence that there's a separation in difficulty between these two problems, the submodular welfare maximization and edge-weighted online bipartite matching. So the main theorem in this paper is that there exists a 0.5086 competitive algorithm for edge-weighted online bipartite matching with Fourier disposal. And the key idea is that we're going to take the greedy algorithm and we're going to add in a little correlated randomness kind of in every step in some way, and then exploit the variance. So this is kind of the highest level takeaway from this talk, is that there's a way to kind of augment greedy with some negative correlation between decisions, and then take advantage of that later on. So that wraps up the intro. Now we're going to talk about the main tool in the paper called online correlated selection. And it's a bit of a standalone problem, and it's sort of a technique that sort of factored out from our algorithm in some way, and can likely be used in other situations. In particular, there's also like a barrier breaking paper, also in Fox 2020, for the AdWords problem, which is a generalization of edge-weighted bipartite matching. And they also used online correlated selection to make that advance. So online correlated selection is the key ingredient for breaking the 1/2 barrier for edge-weighted bipartite matching. And we're going to motivate this technique with the following thought experiment in the unweighted online bipartite matching problem. And this thought experiment is kind of the sequence of, it's kind of how we ended up coming up with this algorithm in the first place, kind of the natural sequence of taking an algorithm, investigating what's wrong with it, coming up with some fix, continuing this process a little bit until we land on something that looks like a way forward. So the first algorithm that we'll analyze is the deterministic greedy algorithm. It's well known that all deterministic greedy algorithms for online bipartite matching are 1/2 competitive at most. And the proof is quite simple. Our kind of toy graph we've been using that we used initially demonstrates this. Basically, when the first vertex arrives, the algorithm is going to match it in some deterministic way. The adversary, however, knows now I can add a second online vertex, and it's going to have one edge to the vertex that was just matched. And because the algorithm is deterministic, it knows for sure that offline vertex will be matched, and yeah, therefore it can kind of break the algorithm. So the algorithm achieves a matching of size 1 on some small instance like this, but in hindsight, and the optimal output is really matching of size 2. So this is the example that shows this fact. Now we're gonna look at a new algorithm, which we'll call two-choice greedy with independent random bits. And the idea here is that we can potentially fix this previous problem by matching to one of the 2 best candidates in each round randomly. So here's the pseudocode for this algorithm. And we're going to step through it and kind of take it slowly, because the final algorithm in this paper really is of the same form and of the same flavor, but there's just some slight changes in principle. So the algorithm works as follows. For each online vertex j that arrives, do the following. Let B be the set of offline vertices adjacent to j that are least likely to have been matched over sort of the history of the algorithm so far, so overall previous random decisions. If this set is empty, we leave j unmatched. There's nothing to match it to. If there are at least 2 candidates, pick lexicographically these 2, I sub 1 and I sub 2, and match j to either of them with independently with probability 1/2. And so independent of previous decisions. So just flip a coin for this round. And now, then thirdly, if there's only 1 candidate, match j to this candidate deterministically. So this is the framework. We either encounter an unmatched round where there's nothing to really add to the objective. There's at least 2 good candidates. We'll choose randomly with a coin flip, an unbiased coin for this round. And then thirdly, there's a single candidate matched to it deterministically. So let's look at this. Let's look at a bit of an example and like how this branches from like a probability point of view. So we take our input graph, and the first vertex that arrives, there's 2 candidates. There have been no previous matches, and this is the first step of the algorithm. So both of these 2 offline vertices are equally good candidates. And so the algorithm flips a coin here. If we take the upper branch, when the second vertex arrives, it's adjacent to the previously matched vertex. However, the algorithm is not adaptive. It doesn't actually know its state. And this is important from like an analysis and tractability point of view. So what happens is, in this case, on the upper branch, when the second vertex arrives, it's adjacent to exactly one vertex that has been involved in some number of randomized rounds. And but because there's only one, it's a deterministic match. And then here, free disposal kicks in. On the bottom branch now, so the first vertex that arrived, it gets matched to the bottom offline vertex. When the second online vertex comes, its match is the top vertex, top offline vertex, and this is unmatched. And so it's able to make this kind of match. So at the end of the day, the bottom branch brings us to kind of the optimal matching. And what this means is that, by the end of the second round, the expected value of the algorithm is 3/2, in contrast to, say, the absolute 1/2 that the deterministic greedy algorithm would achieve. And so kind of a warning, and not even really a warning, but just a note is that the algorithm is actually not adaptive. It's not reacting to kind of the previous chosen candidates kind of in an explicit way. Instead, it makes its decisions based on the expected state of the algorithm over all possible like histories. So all prior random decisions that it's made is kind of simulating all of these together. So this will come in when we start analyzing the online correlated selection tool. And so algorithm 1, though, isn't sufficient. Two-choice greedy with independent random bits is still 1/2 competitive. It's not enough to break the 1/2 barrier even. So we're going to need to do something different than a random coin flip in each step. So algorithm 2 is the following: negative two-choice greedy algorithm with perfect negative correlation. And the idea here is, so we want to do better than a negative coin flip, and we do so like via this negative correlation route. So perfect negative correlation is the following property in this context. Each offline vertex is matched after being a candidate in 2 randomized rounds. So it's matched with probability 1. We know that if an offline vertex has appeared in 2 randomized rounds, it was matched in either the first or the second. When it happens isn't important, but we just know at the end of the second it has been matched. This property is infeasible in general. It's like a very, very hard constraint to satisfy. But we're able to show that two-choice greedy with perfect negative correlation for graphs that like admit a feasibility property, in this case, it is a 5/9 competitive algorithm. And it's tight for this algorithm also, but it's 5/9, so it's greater than 1/2, and it's going to be kind of our way forward when generalizing to the edge-weighted case. So now we're going to investigate kind of this third idea. Can we use partial negative correlation to retain feasibility? So use enough, though, to break this 1/2 barrier. So better than random coin flip, but still maintain feasibility for all possible inputs. Well, the answer is yes, and we do this with the following tool, which we call online correlated selection. So online correlated selection is its own online algorithm that we use as a subroutine, and it's parameterized by a value gamma that sits between 0 and 1. And we say it's gamma semi-OCS is an online algorithm that takes as input a sequence of pair of elements in an online fashion, and it selects one element for each pair online, such that at any time step of the algorithm, if a given element I has appeared k times, the probability that the OCS selected it is greater than or equal to this term on the right, 1 minus 2 to the minus k times 1 minus gamma to the k minus 1. And this gamma factor here, this 1 minus gamma factor, sort of discounts the value of 1/2 to the k. And ultimately what this does is it boosts the probability closer to 1. So it kind of decreases our gap that we would get from random decisions, random coin flips in each step. So the first observation is that it's a generalization of kind of algorithms 1 and 2. In particular, when gamma equals 0, we have like the independent random bits version where we're just doing a coin flip. So the probability is greater than or equal to 1 minus 1/2 to the k. When gamma equals 1, this term ends up being the probability that is selected is equal to 1 if if the element has appeared twice, at least twice. So we're going to find some gamma that sits in between these. That's the hope, at least. But the main theorem in this paper is that we can do that. In fact, there exists a gamma equals 0.1099 OCS. So this is a rather complicated construction, but a simple 1/116th OCS suffices for breaking the 1/2 barrier, and it is really quite a clean construction. And so kind of a one-sentence version of what's happening is that this OCS receives online a sequence of pair of elements, and the OCS sort of constructs like sort of a matching on the fly between different pairs that have a common element. And for a matched pair, it kind of guarantees that one of those common elements is chosen at one point. So that's how we're able to do better than random coin flips. So to illustrate what's happening here, we'll look at a bit of an example. So suppose that the OCS has received at this point up to 3 different pairs. So it's like time step 3. When gamma equals 0.1099, the probability after time step 3 that A has been selected is greater than or equal to this quantity. And notice that it's strictly greater than just flipping a random coin in each step to decide which element to take. And this is kind of the difference. The difference here is that the OCS guarantees us a lower bound of 0.901 as opposed to the purely like independent random 0.875. Similarly, B has appeared in 2 of the pairs, so it is doing a little bit better than random. And then C has appeared in exactly 1 pair. And so we don't really get the OCS guarantee until it's appeared at least twice. Okay, so this is the OCS. It's a standalone problem. This is the main takeaway as far as techniques. And now we're going to dive into the algorithm and the analysis, kind of at a bird's eye view. But although it's not going to be a high-level kind of overview on what we do here, I think it will provide a fair amount of context for when you go and read this paper. And so it should make kind of the initial read quite a bit easier. So we use 2 main tools to achieve our algorithm. The first is the online primal-dual method of Devenard et al. In sort of 2013. Second, we use the complementary CDF viewpoint of a probability distribution introduced by Devenard et al. In 2016. And then we introduce our new tool, which we call online correlated selection, to kind of break the 1/2 barrier. And in particular, our algorithm uses a gamma OCS as a black box, and the competitive ratio of our algorithm depends purely as a function of gamma. So improving OCS constructions is going to translate to better online matching algorithms, kind of by default. So we start with the online primal-dual method. This framework, so first we'll introduce the matching linear program and its dual. The matching linear program is on the left. This is kind of a standard construction, and its dual is on the right. And we'll note that in the dual, there are dual variables, a single dual variable for each offline vertex and a single dual variable for each online vertex. And the constraint initially is that the sum of these 2 for each edge is greater than that edge weight. This is kind of the edge weighted version. And our algorithm is going to basically kind of increment and kind of maintain these dual variables in such a way that an approximate version of this is satisfied to give us a final guarantee. Now, the main observation here is that in the primal, if xij is defined to be the probability that edge ij is the heaviest edge matched to I, then the primal objective is going to be equal to the output of the algorithm, so the expected matching that the algorithm gives. And this is just by definition if you choose x sub ij to be this. But what does that mean? Well, we'll see in a couple slides, but this is kind of the route we end up taking. So to plug into the online primal-dual framework, we're actually going to build off first build off this lemma. So the online primal-dual method says the following. Suppose an online algorithm maintains a primal and dual assignment, not necessarily feasible to the original problem, such that for some gamma between 0 and 1, the following always holds. First, the notion of approximate dual feasibility. So for each edge, the sum of the incident offline and online vertices are greater than or equal to gamma times the weight of that edge. Here, gamma is a bit of a discount factor. It introduces slack. Right, so yeah, and we're going to ultimately try and optimize this gamma value. Second, we need this reverse weak duality property. So the expected value of the algorithm is greater than or equal to the primal objective of the assignment. The objective of the primal assignment, which is greater than or equal to the objective of the primal-dual assignment. So these aren't necessarily the values per se, but they're the values of the assignment that the algorithm maintains. If these conditions are satisfied in each step, then the algorithm is gamma competitive. So this is the game we play. We build off this framework, and the goal here is to design feasible increments at each step of the algorithm to the dual variables for some gamma strictly larger than 1/2. So we're going to work from here. Now, the expected output of the algorithm is roughly the, for the previous definition of xij that we saw earlier, it's equal to the primal objective. And we can rewrite this as the sum over all offline vertices, summing up their expected heaviest edge weight. And this is really just like the free disposal assumption coming into play here. Because ultimately, yeah, we're going to take one edge and we're going to take the best. Now what we can do, the complementary CDF viewpoint, is really a way to sort of decompose this expected heaviest match. And it does so by creating a function over all edge weights. So we're going to integrate edge weights from 0 to infinity, and the function value is going to be the probability that I is matched to a vertex of at least W. Okay, and we're going to kind of cleanly, for now, remap this probability to a function called y sub I of W. So this y sub I of W is the same definition we saw before, but what is it? Well, again, it's just going to be some step function kind of sitting over every offline vertex, and then the input to the function is the weight, and it guarantees this property. So what happens over the course of the algorithm is that initially we have some step function that's 0, and when an offline vertex is involved in a randomized round with an edge of a given weight W, the function values are incremented in some way because there's a probability that that offline vertex gets that match. Alternatively, which we see kind of in the bottom right figure here, is that if an offline vertex is involved in a deterministic round for a given edge weight, then for the y sub I function, it gets incremented to 1 all the way between 0 and the edge weight that just got deterministically matched. So this is just this function that kind of keeps track of what's happening. But it's a piecewise constant function. Now, the updates to the dual variables look like the following. We're going to take our offline dual variables, alpha sub I, and we're going to decompose it kind of in a similar way to this, this y sub I probability. So the dual variables now are going to get remapped to like a dual variable function. And we're looking at the approximate feasibility constraint. So now we're dealing with the dual variable function alpha sub I of W. Again, it's piecewise constant in kind of a similar way. And when I, the offline vertex, is involved in a randomized round, we increment this value kind of in a systematic way, similar to what we just talked about. And it's actually quite easy to keep track of because it's, the only discontinuities occur at previously encountered edges, and ultimately it's just this piecewise constant function that's easy to maintain. So again, as the offline vertices are involved in either deterministic or randomized rounds, this alpha gets incremented in some systematic way. And then we ultimately compute the values in which are incremented. Now the online dual variables are initially 0. When the online vertex comes, then it's just incremented once according to some formula. So that's just kind of what happens behind the scenes. But the edge-weighted matching algorithm, in principle, is very similar to algorithm 1 that we saw before, two-choice greedy with random decisions. So when an online vertex comes, the algorithm computes marginal gains for each offline vertex. And this includes deterministic and randomized marginal gains. Then the algorithm branches as follows. If the best randomized gain and the best deterministic gain are negative, do nothing. It's an unmatched round. If the best randomized gain is better than the best deterministic gain, let the OCS decide how to assign the online vertex. And it takes the two offline vertices that have the highest randomized gain, and then it just makes this decision kind of as an input to the OCS. So that is the pair we feed to the OCS. If the deterministic gain is greater than the best randomized gain, then we just greedily assign the online vertex to the offline vertex that has the highest deterministic gain. So this is kind of what's happening. Again, we count an unmatched round if there's no marginal gain to be had. If the randomized gain is good for some computable notion of randomized gain, we let the OCS make the decision. And then if the deterministic gain is going to be good, we make a greedy decision. Now this is the algorithm in the paper, not exactly necessary to digest, but I want to point out a couple of things for a read through. This case of I is really the only state that the algorithm maintains. It's the number of times an offline vertex has been involved in a randomized round with a given, with a given kind of edge weight threshold. And this is what connects us to the OCS probability, because the OCS guarantees us, some probability having been chosen given for like a certain number of times that has been a part of the sequence. Now, the deterministic and randomized gains really, like kind of at first glance, are these integrals that we see, but really these are integrals of constant values. And so these constant values are given in the paper as well. These are the increments to the dual variables, and they're optimized offline via factor revealing linear program. So my point in presenting all of this is that this is actually all that's necessary for the algorithm and to implement an algorithm that is better than greedy, just these pieces. And this is kind of how they tie together. So lastly, I want to kind of just say at a high level what happens with the analysis. So we have to connect the primal objective to the OCS bounds, and we do so with a bit of a surrogate. But there's nothing really complicated going on here. It's mostly bookkeeping. Second, we want to optimize the approximate feasibility constraints from the online primal-dual framework. And we do so with a factor revealing LP. So the goal here is to find the highest value gamma where we still maintain approximate feasibility. And then thirdly, we need to construct and analyze the gamma OCS. And that kind of is a standalone analysis. So I'll point out that the factor revealing LP is quite of a cool tool that we use here. But the goal, again, is to maximize the competitive ratio. And to do so, the OCS terms end up appearing in some of the constraints for approximate dual feasibility. And I'll just note that if these, in the case of a zero OCS, so it's just kind of the independent random coin flips each turn, then ultimately the output here is going to be 0.5. But once we have a positive gamma, so some non-trivial construction, then we're able to get a capital gamma that's greater than 1/2 the competitive ratio. And so that's where these table of values are coming from when we have like these pre-computed dual variable increments. So to end, I'll just discuss some open problems. But the main problems from this paper are, well, what is the largest achievable gamma for an OCS construction? We know that 5/9, the hardness that we get from 5/9 means that 1 is not going to work. 2, is a multi-OCS useful? If the algorithm considers a set greater than 2 in each step, can that buy us something? It's going to be harder to analyze though. 3, more applications of OCS period. It helps break the AdWords problem, the 1/2 barrier in the AdWords as well. So it seems to be quite useful for online optimization. And then fourth, we're going to need new techniques to beat the 5/9 competitive ratio period, assuming that the upper bound for this problem is 1 - 1/e. And if it's not, what is the true upper bound? So with that, I'm going to end the talk. Say thanks for your attention. And yeah, if you have any questions about this paper or these results, feel free to reach out. Yeah, so take care and have a good rest of your day.